Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a second video in a series on limit laws for differential calculus students. We've just introduced ourselves to the limit laws. In fact, in the previous video, we learned, I don't know how many of them there are, maybe about 10 of them, something like that. But we learned all of them. Now we're going to go ahead and use them in great detail. Normally, you don't have to use them in great detail. However, initially when you're learning them, it's so good to learn how to go through them step by step, justifying each step of the way. So let's go ahead and evaluate this limit using the limit laws, if possible. That's the key phrase there, if possible. Otherwise, we're just not going to evaluate the limit. So let's go ahead and start seeing what we could do. Now, to remind you, we have all these limit laws that we introduced ourselves to last time. What is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh yeah, there are 10 of them. And you can use them as long as the functions who you're taking limits of exist and are finite. That's critical. So let's go ahead and see what happens in this problem. So I take a look at this limit and I say, I'd really like to use the limit laws here. I see that it's sort of a difference between two functions. In fact, it's very much like a limit as x is approaching 5 of a function minus another function, where f of x is x squared and g of x, well, that's 1 over x minus 5. We can go ahead and use the limit law to try to split this limit. Now, I might have mentioned this in the previous video, but if I didn't, I'm going to state it right now. It's okay for you to try to split a limit, but the moment that you find that one of those splits that you split the limit into is not finite and is not infinite, in other words, that it does not exist, that's when you know you took a wrong turn and you have to glue everything back together and try something else. So in this case, I'm going to try to use the limit law that allows me to split apart a difference of functions. So this is basically the limit law that says the limit of a difference is the difference of the limits. Notice that I put a question mark on the equal sign there, and the reason why is I'm not 100% sure that we can break this apart. Well, okay, I'm 100% sure that we actually cannot, but I'm pretending as though I'm a student, that I'm breaking this apart, but I'm not 100% sure that I can. So I just let myself know that's questionable what I've just done. Let's go ahead and insert the functions that we're dealing with here. So there we have done that. The leftmost, and I'll still keep the question mark up there. The leftmost function I'm actually not going to mess with because there's something that we need to note about the rightmost function. This rightmost function, if you allow x to go to 5, that's going to be a massive issue. In fact, if you did any more splits with this, if you broke it into a quotient to where you had the limit as x approaches 5 of the numerator divided by the limit as x approaches 5 of the denominator, you would find out that denominator tends to 0. In fact, let me go ahead and just do that since I have the time. Notice that I'm slowly breaking it apart into its component pieces. I split the functions up, and then on the second limit, I split that fraction into numerator and denominator. But at this point right here, I know there's going to be an issue. That limit in that denominator is going to tend to 0. And the limit law that we're trying to use, which is this guy right here, tells us that you can totally break apart that limit if you want to, as long as the limit of the denominator's non-zero. But unfortunately, that is what's happening in our situation here. The limit of this denominator is tending to 0, and that's a bad thing. This tells us that we could not have split this apart. This was an illegal split right here, and that was born of, technically, this illegal split right here. Because The first term in that split, the limit as x approaches 5 of f of x, well, that's okay. That's actually going to be 25 in the long run. But the limit as x approaches 5 of g of x, which is the limit as x approaches 5 of 1 over x minus 5, that does not exist. And therefore, you cannot use a limit law to evaluate this limit, at least as written. Now, we might come back to this problem later, but I'm just going to tell you right now, this limit does not exist. There's just nothing you can do with it. But we might have a chance to come back to this later. Anything else we do with this would not be instructive. Just as a heads up, if you try to break up a limit as you go through and you're trying to use the limit laws, when you try to break limits, always check to see that the component limits that you've broken things into exist. If they don't exist and they're not finite, then all bets are off. You have to glue everything back together and start at the beginning. That's going to be a theme in calculus. You're always allowed to try to split a limit, but the moment that you find out that one of those splits is not finite and not infinite, that's when you have to go back to the drawing board. Now let's focus our efforts on a limit that we can evaluate. And this time I'm going to list out every single step here. These are arduous when you do this. So I'm just letting you know, I do expect my students to do at least one limit where they list out every little step along the way. But once you get proficient with working with limits, you can kind of shed that rigor and just evaluate limits quickly. But let's go ahead and step by step go through this, just to showcase really how you would want to do limits rigorously. So the first thing I'm going to do is say this is equal to, we have a limit law, and every time that you use a limit law, you're kind of crossing your fingers and hoping that you're allowed to use it. So I'm going to put a little question mark here. I'm not 100% sure this is legal. It's only legal if in the end everything becomes finite. But for right now, it's just us crossing our fingers and hoping. We have a limit law that says the limit as x approaches a of the nth root of your function, you can actually rewrite that as the nth root of the limit. And remember, the power or the index on your radical n must be a natural number, and the function must be greater than or equal to 0 if it's an even limit or an even index, which might be the case here. Who knows? I'll just move the square root outside of the limit, and I'll write this as the square root of the limit rather than the limit of the square root. Now we're crossing our fingers for one thing right now. The thing we're crossing our fingers for is that hopefully that limit is not going to be negative. If it is, we've got problems. Now what I'm going to do from this point forward is every time that we have a concrete thing that's been moved outside of the limit, I'll write that in green. Now what I'm going to do is split this limit, this guy right here, I'm going to split that into both numerator and denominator using this limit law right here. So I'm allowed to split a quotient, the limit of a quotient, into the quotient of limits as long as the denominator does not tend to 0. And by the way, I should probably have written out the justification earlier. So the first one we used the root of functions limit law, and this is going to be the quotient of functions limit law. So there we have that. Now we're going to use the quotient of functions limit law. And I'll zoom in so I can write the quotient out. All right, now again, in this case, we're now additionally hoping, remember in the first case, we hoped that our radical was, or a radicand at least, was not negative. Now we're additionally hoping that that denominator is non-zero. All right, let's go ahead and go further. I'll work on both numerator and denominator simultaneously. So in the numerator, I'm going to split this limit into 3 separate limits here. It's not distribution, you're just splitting the limit into the sum or difference of 3 different functions. In the denominator, we're going to use the power law for limits, which is the limit as t goes to 5 of t to the 4th is going to be the 4th power of the limit as t goes to 5. So let's go ahead and write those down. And again, just to justify this here, I'll go ahead and go back and note that in the numerator, we use this power law right, or limit law right here. The limit as x approaches a of the sum or difference of functions is the difference or sum of those functions. And again, that's called the sum or difference limit law. The other one we used was this guy right here. The limit as x approaches a, although we were dealing with t. So the limit as t approaches a of t to the nth. Well, that one is actually going to be t to the nth. I could have just written that as a to the nth power. So I should probably have done that. I'll go ahead and do that. I'll go back and erase and clean that up. So that's a limit of a power function law and the sum or difference limit law. And there you see I've actually cleaned it up and I've justified off to the right hand side. Now let's see what else we can do. Well, I'm actually going to apply that limit of a power function limit law again. So as t approaches 5 of t squared, that'll be just 5 squared. This guy right here, we're going to go ahead and factor out the 5. That's a constant multiple limit law. And this guy right here is the limit of a constant limit law. So let's go ahead and write that stuff down. Before I get too far, I just want to mention that question mark is still there because I'm not sure if this is going to be negative underneath that even root or not. There's still that big questionable piece. So let's see what laws I used here. The first law, the 5 squared right there, that's just a repeat of the limit of a power function law. The next one in line is this constant multiple law. At least that's what I think I call it. Yeah, constant product limit law. And then we also have the limit of a constant law that we used after that, the limit as t approached 5 of 16. So there we have our justifications there. Now, a lot of students really dislike the level of detail that's going on here, but there is something very special about this that you have to understand. And if your calculus instructor, maybe you took it in high school or something like that, didn't enforce this, it's because they didn't believe that you would ever make it to higher level mathematics. But I'm telling you, I believe that you can make it to higher level mathematics. You just have to show patience and attention to detail. And that's exactly what this process is all about. So let's go ahead and rewrite all this. I'll put the equal sign with the question mark. And I left that blank space near to the 5 in the middle area because I want to talk about that. That's the identity limit law, the limit as t approaches 5 of t. As t gets really close to 5, what does t get close to? Well, if you said it out loud, you're right, 5. So this is going to turn into 5. And again, it comes from this limit law right here, which is the identity limit law. Zoom out so you can see that. And now, if everything is well and good here, then hopefully that radicand is positive, which it is actually. So I am now going to just say this is definitely equal to, in fact, I'll write that in green as well, the square root of 25 minus 25 plus 16 over 625. Square root of 16 is 4. Square root of 625 is 25. This is 4/25. Now, something you need to note about this, a lot of students will say, you know, that's exactly what I got when I just plugged in 5. And it is true. Had you just plugged 5 into this function here, you would have gotten to that same answer. However, it's illegal to do that until you've been given the permission to do so via a theorem. And that's what the next video is all about. The theorem is called direct substitution. You cannot always use it, but you can sometimes use it. And we'll see that in the next video. For now, we're done with this. Before we go, I just want to tell you that it's not the case that you have to justify like this every single problem. Only do so if your instructor says on this problem, justify every step. So I do that in one of my homework problems, but it gets monotonous, very tedious if I have you do it every single problem. However, it is a good exercise in logic to take your time through a limit every once in a while. All right, hopefully I'll see you in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.